All right, welcome. I want to just continue in this video, like we've done in the last two videos, talking about loop invariants and the correctness of simple algorithms. And so we focused mostly on algorithms we've probably seen before, and I'm going to continue with that by looking at an algorithm to solve the problem for string equals, which is just a simple way of saying comparing if two strings are equal. All right, so let's take a look at it. Let's first, as we've done so far, let's try and characterize the problem, as a information processing problem or a computer science problem, meaning as a relationship between an input and an output. And so that's what we have here again. Let's take a moment to just take a look at this. So again, we're using similar type of inputs that we've seen thus far. The last two problems we looked at were problems about sequences of integers. The string problem is about strings, which are sequences of characters. And remember in that earlier video, I mentioned that just notationally, we tend to write strings different than we write sequences of other things, like sequences of integers, even though functionally from a information processing perspective, they're exactly the same thing. They're just sequences. And so here we just sort of are writing it using the notation, the mathematical notation that is consistent with the topic or the subject matter that we're working in. We're talking about strings, so we'll write them to look like strings. If we're talking about sequences of integers, we'll write them to look like sequences and so on. So in this case, we really are just dealing with lists. If you think of them from the computer science perspective, these are just lists. But again, mathematically and notationally, we might have different ways of referencing them. Okay, so this is a kind of interesting and true a yes-no answer. We sometimes call these problems decision problems, where you have a binary output, an output that is yes, no, true, false, 0, 1, something like that. And sometimes that's all we care about a particular problem is a yes, no. So for this particular problem, we've got two strings and we just want to know if they're equal or not. Sometimes when we approach this problem, and in fact some solutions to this problem, want to know more than if they're just equal or not. Sometimes we want to know if they're equal or not, and then if they're not equal, we want to know a little bit more, specifically, well, which one's bigger or which one's smaller. And not all data types have the biggerness or smallerness relation defined on them. Numbers do, of course. That's where we get the relationship from. We borrow that from our natural numbers. But then for strings, at least strings of alphabetic characters, so words, we have developed what we might call a conventional ordering for them. First of all, the characters themselves have a conventional ordering. If you learned the song when you were little, A, B, C, D, E, F, G, that song tells us the order that the characters go in, but there was no reason they had to go in that order. They just happened to go. That was a convention, that was a choice that someone, I presume, long ago made that choice when they started singing that song, probably. And so now we just follow that convention, and guess what? We'll teach it to the next generation as well. That's how conventions sort of work. Okay, they happen to be that way just because they happen to be that way. And why do they happen to be that way? Well, because they just continue to happen to be that way. And then we borrow from that for strings, of course. A, B, C, D is how we letter the characters, but then think of a dictionary or a phone book. I know those are turning into ancient pieces of technology, but in such books, we will have a bunch of words or names ordered in what we will often call lexicographic order, which is borrowing, again, this idea of putting things in order and applying it onto words. What order should we put them in their lexicographic order? Just means their dictionary order. And so, again, this is something that might be implied upon different types of data types that we can put them in an order. Okay. Now that was a little aside here. We were just talking about the string equals problem and why we might be concerned about the false side here. I mentioned in the last one, sometimes when the answer is true, we want to know more about it. In the last example, we were searching for an element. So if the answer was true, yes, we found it, we wanted to know more. We wanted to know, where did we find it? Sometimes, though, the extra information comes on the false side, which is what we have potentially, at least for the string equals, which is if they're equals, we'll answer true, but then if they're not equal, we want to know which one is bigger than the other. And I've left that out of this problem statement. Sometimes we want to know that, but I just left it out. And as a result, what we result in is a pure decision problem, one where our outputs are just yes, no. Decision problem just means binary output. Okay, so here we have a pretty cool and interesting decision problem, detecting if two strings are equal or not. Again, maybe in your investigation, your studies up till this point, you've already had an opportunity to maybe write some code for this, or at least work with functions that compute this. And now we can see how we might do that, and can we show that is correct. Again, like I mentioned for the last couple of videos, we will be counting operations down the road, but for this video, we're going to stop here after proving it's correct. Okay, let's go. All right, let's think about the algorithm. And maybe if we've been thinking, what were those last two algorithms we did, minimum and what was it, sequential search? Both of them, they kind of have the same style as the algorithm we might have here, which is we're going to start at the beginning of the sequence. In this case, it's a string. And we're going to do something as we go, one step as we go along. Okay. What are we going to do that's different then? Okay. If we're comparing our two strings and we want to make sure they're equal, what are we doing is we want to compare our AI to our BI, or our AJ to our BJ, and so on, A1 to B1, A2 to B2, and so on, to do what? To make sure they're the same. If we want to answer true, they all have to be the same. And there's a little subtlety too here. The N then has to be the same as the M too, right? I guess I should highlight here that I was conscious when I wrote down this input here to make N and M different, because it's possible they are. It's possible the two strings we're handed are of different length. Well, if they are actually equal, we know they are the same length. And if they are actually equal, then we, as I was mentioning, they also have the exact same characters. And that's what we might do in our algorithm. So let's take a look at the pseudocode that I've come up with here. And again, the pseudocode you might have come up with is different, and it might still be correct, which is great. There's multiple different algorithms that are correct for a particular problem. And so just because yours maybe looks a little different than mine doesn't mean it's not correct. You might need to modify your proof a little bit to make your proof work for your code instead of mine. But you should probably easily be able to make that argument as well with, again, maybe a pivot here or there of how you make the argument. Now let's take a look. I mentioned this in the last video as well. I've chosen to use a flag here. I'm calling it R for return. And this flag R is going to be set. I'm going to set it up ahead of time to be true, meaning the assumption that I'm going to have is that the two strings that I have are indeed equal. But anytime I detect evidence that they are not equal of any kind, I will flip this flag to false. That's the idea I have behind the algorithm. Now remember, that idea is important because it's the idea behind the design, but it's also the important piece to the proof. That idea that we put into our design, if that idea is correct, also comes back again in the proof to be the key piece that we put in the proof that says, see, this is why it's correct. If effectively what we're saying is the reason is correct is because I designed it to be correct, which of course makes sense. We are engineers in the sense that we are designing these algorithms for a purpose, and we shouldn't be that surprised if we succeed. Of course, that was the goal, to design them for the purpose. So that's why that design principle shows up again in the proof afterwards. If we're trying to convince someone that we did it right, we say, see, this is the design principle I used, and use your own intelligence and reasoning skills to determine if that design principle is sound. Okay, so let's go ahead and look closer at my code here. I mentioned I've got this flag here, R, that's going to be true. Eventually I return it only if they're equal. The first thing I do is I check to see if the length is the same or not. And this is actually maybe not necessary. It's sort of like an early termination. Maybe this is just to make sure that if we have different length, we don't waste a lot of time in this loop down below. Okay, we might still loop through the way I've written it here. If this was an early return statement, we might get out of the way. But the way I've written it will still enter that loop. But really, as I mentioned, it's sort of like an early case detecting. If they're not the same length, we know they're not the same, and we're done. Now, why might I have added that there? And I may be trying to think to myself why I added it there, is I was thinking, I think what happened is a little bit of my implementation details started to creep into my algorithm, and I try and do that as little as possible because implementation details are details, and we often want to eliminate as many of them as possible. And here I think what I was thinking was about, well, if I don't do a check ahead of time that they're the same length, I might get an out of bounds error down here. I might get some kind of segmentation fault going on down here. And this is where I need to stop myself. And maybe you might stop yourself too. That's really important if you're writing code, but we're not. We're writing an algorithm here. So there are no segmentation faults. Okay, your algorithm might not make sense, and someone might read it and say, hey, that's out of bounds and that doesn't make sense to me. But usually if we allow our algorithms or our pseudocode to have potential for out of bounds access, which again is usually causes an error of some kind, we'll assume that that error is handled by the whoever implements it. We're going to assume they implement it in a way that we'll tackle those implementation details when we implement it. We won't do it now. Meaning I could possibly eliminate this line here. If I eliminate it, we might say, oh no, what's going to happen then? We're jumping right in here to this loop. I might have to change the n to something like max of n and m, something like that, I'm not sure. But we could just say, well, what happens down here when we get out of bounds? Okay, let's say we were iterating through, let's say m is 0, so there are no b's. So we get in here, and the first thing that happens, we go a1 is equal to b1. Now again, hopefully a lot of us are probably programmers, so already we're being like, oh no, it's going to crash. The machine should just be like, there's nothing there, whatever error your favorite programming language throws for that particular error, right? So we might have that already built in and say that's not going to work, and so we might fix our code. That's where I think this line came from, when I was already thinking, hey, I need to fix something here. But we should follow that principle. Let's assume the implementer would handle this however they want. Well, if the element there, if say the b is not there, then how is this line supposed to go? Well, is ai equal to bi if it's not there? No, it's not. It's not equal if one of them is missing, so we should set the flag to false. So we could say, assume reasonably that entering into this pseudocode, we actually didn't need to do this check and don't need to worry about out of bounds calls, because we'll assume all those out of bounds checks just trigger this if and set our r to false. So whenever that happens, we'll set our r to false. Now again, I mentioned this only as an aside. I've written the code the way I've written it here, so this is the code that I'm going to write my proof on. Okay. But the reason I mentioned this aside now is I looked at this line and I thought to myself, now as I'm about to talk about it, hey, I might be able to eliminate that line too. And when my brain says, hey, I could eliminate that line, that says, hey, that's simpler. And if that's simpler, then why not go with the simpler one? But, oh well, this is what I've got here, so we'll instead use that as a lesson for how we might be able to simplify things even further in the future. But let's go with what we've got here. Okay, so as I mentioned, at this point we're just checking the size. Are they the same length? If not, boom, we already set it to false. But then we enter here, and I mentioned it already. Here we're checking to see if they're equal. If we find any two that are not equal, we'll set our flag to false as well. So we're going along the line, B1 and A1 are the same, B2 and A2 are the same, B2 and A3 are not, boom, we set our flag to false. And as I already mentioned, maybe we run off, we end up, there's no B's left, or there's no A's left, whichever one. If we get an out of bounds error, boom, we set it to false. Okay. And then at the end, we're supposed to return R. Now again, you've heard my design strategy here saying why I've designed it this way. R will remain true unless we find evidence that they're not equal, at which point we'll flip it to false. As long as I've done that correctly, then this should be a correct algorithm. So let's see if we can, take this algorithm and argue that. So again, to do that, we can't go straight to the correctness argument. We need to, well, at least the standard way is to go through this loop invariant. So we're going to come up with a principle or a property that is true about this loop after every iteration of the loop. And then prove that property true. That property will help us prove correctness for the whole algorithm. Okay, so again, that's what that is. And again, I'll sort of give the same lesson again. There are many properties that are true after every iteration of the loop because there are many things that just are not related to the loop. Okay, the sky is blue. That will be true after every iteration of the loop, I hope. But it is completely irrelevant. It is unrelated to the loop, and it's not going to help us prove what our ultimate purpose and goal is, which is prove that this algorithm is correct for the string equals problem. And I keep mentioning this, that we want to keep our purpose in mind, and this is true both in programming and in mathematics, that we're not usually just doing it for fun. Sometimes we are, which is great, then have fun. But if you're not doing it for fun, you're doing it with something in mind. And usually that purpose is a great way to inform us what tools we should use, what notation we should use, maybe what programming language we should use if we're programming. Whatever it is, whatever that purpose, that ultimate purpose is, helps us inform us what we want to do. And so again, that's the principle I want to bring to bear here on the loop invariant. What is the purpose? We're trying to prove this correct. So what property of the variables of this algorithm might we want to know more about? Well, let's again focus in. Remember we did this last time. Well, R is the thing that we're going to return. So maybe this property should have something to do with R. And the other thing we'll notice is R here, because we're dealing with this decision problem with the Boolean output, the yes, no, 1, 0, true or false here, that R is only going to be true or false. At least that's what it looks like from our code, and that would be, maybe I've already honed in here on part of that loop invariant. I said R is always going to be true or false. I might just write that down in my little scratch notes on the side. R is always true or false. Is that the principle that's going to be helpful? Actually, that would be helpful. That means at least with that information that R is always true or false, and the fact that we return R, at least we could argue that we always output true or false. We never output 1 or 23 or the alphabet or some other weird thing. We output Boolean answers. That's good. At least we're on the right track to correctness. But is that enough to establish correctness? No, because we still need to argue that we answer true and false when we're supposed to, when we should, when it's correct to. Okay, and that's where, again, going back to that problem statement telling us, yes, we answer yes if A equals B and no otherwise, right? True, I guess, if A equals B, and false otherwise, okay? So just knowing that R is always true and false is maybe not enough. So what else do we need to know? We need to know that R is true when some other property is true, and then R is false when some other property is also true or false. Okay, so what are those other properties that we want to bring along? Now this is again going to create the same sort of structure we saw in that last video where we have sort of two cases we could be in. Either R is true and something is happening, or R is false and something is happening. Okay, so again, how we code this out, how we formalize those statements is going to help us. There are maybe ways we could do it that maybe cause extra work for ourselves, and then ways we can do it that make it easier. So sometimes we go through a process of recasting these statements over and over again in different forms until they're in the form that we like. So I'm going to let's focus on maybe R true first. I just picked it out of the blue. It might not be the easier case, okay? So R true first. What happens if R is true? Well, let's think about the problem statement. If R is true, that means that if we answer R is true at the end, what does that mean? That means A equals B, right? But remember, in the last two algorithms, we had an M variable where the M was keeping track of something so far. And that's what I want us to highlight here as well. Something's going on so far as we go through this loop. And what is it? We're comparing A1 to B1, and then A2 to B2, and so on. If R is still true after, say, iteration I, meaning we didn't flip it false here and we didn't flip it false here in any of those iterations, then there is something that we know so far. We know that A is equal to B so far, right? Meaning we've never hit this not equal to bit. Or a more formal way of saying that is we know that A1 is equal to B1 and A2 is equal to B2 all the way up to AI is equal to BI for iteration I. After iteration I, we have confirmed that last piece. Okay, so that's the R is true bit. R is true, and so far our symbols are the same. Plus one little piece about this too, and we know n equals m, but that part might not be as important. So what about the R equals false case? Well, R equals false case, there are some other properties that may be true. R equals false means either we know that n is not equal to m, maybe before the loop even happened we flip this off, right? Or if R equals false, it means somewhere along the way in one of our iterations we found a mismatch and we flipped it false. And that's kind of a complicated statement because it has a bunch of different pieces. Maybe that's the problem with it. It's comprised of different parts. The part about maybe them being of different length, and then the part about them having a mismatch. And then if we start focusing in on that mismatch, we might say, well, when was the mismatch? How many mismatches were there? Because every time we get a mismatch, we might flip it false again. Of course, flipping a false doesn't do anything, but if we get into the weeds there and get lost, we might say, oh, there's a lot of details there. But if we back ourselves out a bit, we might look at those details and say, but all those details mean the same thing. All those details imply that A is not equal to B. If they don't have the same length, then A is not equal to B. If they have a mismatch, then A is not equal to B. And why is that way of expressing it, useful for us or helpful for us, is it still does the job we want. We want to say that when R is false, what do we need to argue? We might go back to the problem statement and go look it up. When were we supposed to answer false? We were supposed to answer false if A is not equal to B. Well, that's exactly what these principles or these properties are telling us here. So here's the way I've decided I'm going to cache this out. Again, you'll notice the structure of this looks very similar to the last problem. After iteration I of the loop, okay, either we're in one of these two cases. And these two cases pivot based on what we've written for our value R. If R is true, then we have matches all the way up to I. If R is false, A is not equal to B. Remember, this is going to help us argue, well, maybe we'll ask the question, is this going to help us argue that our algorithm is correct? Well, if we end up in case 2 at the end, our R is false, that's what we're supposed to respond when A is not equal to B. So that would help us. Also, if at the end we end up with R equal true after the last iteration, then I replaced here with N is exactly the condition for when they're equal. So it looks like we've got this set up in a way that will help us with our proof of correctness. So let's try and prove this with some induction. Again, I'm going to set it up in the same way as we've done previously. I'm going to tell you I'm doing induction on I here, and we're going to start us off with a base case. Remember, the base case is the specific case where we're going to establish what happens before the loop occurs. Okay, again, our loop started here, I equals 1, so the base case will be I equals 0, prior to the loop. Okay, so what happened prior to the loop? Well, remember, prior to the loop, I had that special line that I thought maybe I should delete. Why did I think I might delete it? Well, I thought I might delete it because it might make this little argument here shorter. And then if I can make this argument shorter, make the whole proof shorter, makes it easier to understand, maybe, a handful of extra students say, oh, yeah, that did make sense. That maybe, got bogged down on this little extra complexity. However, this complexity is honestly fairly simple, so hopefully we're going to get through it. So let's see if we move through. So what did we say? I said before the loop, what happened? Well, the very first thing we do before the loop is we set r to true, but then we do that check. If n is not equal to m, then we set it false. But notice, if n is not equal to m and we set it false, in this case, a is not equal to b. So after, or rather prior to the loop, r is equal to false and a is not equal to b if this were the case. So what about if this was not the case? If this was not the case, then if n is equal to m, then we set r to be true at the beginning. And then, if r is true, we want this statement to be true. But notice, I've got this statement rewritten here again. aj is equal to b for all 1 less than or equal to j less than or equal to I. I've got the statement here saying that this is vacuously true because I is 0. So there's nothing to prove here. There are no values of j in that range, so there's nothing we need to confirm here. This is a tautology, a statement that will be true no matter what when I is 0. So we're done. If r is true, there's nothing for us to prove. If r is false, we've confirmed that they're not equal, so we're good. So let's move on to the inductive hypothesis. Now remember, the inductive hypothesis is going to try and establish for us that whatever happened in iteration I worked, so whatever this property is true after iteration I, but now we're going to focus on iteration I plus 1. Okay, so we're going to assume that prior to this iteration that we're working on here, I plus 1, which is again also after iteration I, we're going to restate what we've got stated here. Okay, so you notice I've just sort of copied down what we've got stated here. So we're assuming that coming into this current iteration, iteration I plus 1, that everything's been working fine, that our theorem is true. And now we'll argue that if it was true on the last one, it must be true on the next one too. And that's what, again, it gets the inductive machinery working. Like the last video and the last proof, these two statements here, or these two cases that we might be in this either, are the two cases we need to consider in our proof. So when we get into our inductive step, where we want to apply the inductive hypothesis, as I mentioned here, we're going to end up having two cases. So prior to this iteration, we're either going to be in the r equals true case, where we've confirmed something so far, or we'll be in the r equals false case, where we've already got evidence that they're not equal to each other. So those are the two cases I want to consider, and again, I'll do that on the next slide, one at a time. So let's start the first one. So maybe let's think to ourselves, which one of these is going to be easier for us to prove? Okay, which one is going to be easier for us to prove? Now, in the last time, one of them was easier when once we've sort of established that state, we can't get out of it. And that's going to be true for, again, our state 2 here, which is once we've set r false, there's nowhere in our code where we set it back true again. We set it true at the beginning, but there's nowhere else where we set it true again. So once it's false for good. And then we also notice that that's true of this extra property here too, that once we know that a is not equal to b, there's no way to make it equal again. We've already got evidence it's not. There's no way it could be equal. So that might be the easier case. So that's the one I'm going to start out with here. Okay, r is false and a is not equal to b. So if already prior to this iteration, prior to iteration I plus 1, we've already set it false, then we've set it false because a is not equal to b. Now this remains the case after the iteration, no matter what we do in that iteration. We might find another mismatch and try and overwrite a false with a false, but that does nothing. And also, no matter what we discover in that next iteration, cannot overwrite the fact that we already know a is not equal to b. So this is the trivial case, the simple case. Once we've set it to false, nothing in our code can unset it to false. But also, once we've set it to false, we already have established that they're not equal. Okay, the other case then will be the trickier one. Why is it maybe a little bit trickier? Well, because we have to split it into subcases. Oops, I got a typo here, called it subcase 1. I'll have to fix that. But oh, I got both of them here. Look at my numbers. That's what happens when you cut and paste your slides. The reason why the r's true case is a little bit trickier is because we actually have two possible outcomes. Is after the iteration, it might still be true, meaning we've confirmed something else. But also after the iteration, we may have flipped it false, Remember, our argument up here is there was no way we flip a false back to true, but here there is a way to flip a true false. And that's why we end up with two subcases down here. So let's look at our two subcases. Let's imagine for the moment they were numbered properly. So the first subcase I chose is, well, so now we're focusing in. Why do we need subcases? It depends on what happens in this iteration. In this iteration, we're actually going to compare AI plus 1 to BI plus 1, right? And if they're actually equal, that's what we're trying to confirm here, then we don't change anything. We leave our true true. So in this case, if they're equal, we leave it true. But now, let's just see, we already knew in this case that they were all equal up to I. We've confirmed that index I plus 1 is also equal. So we've now confirmed it all the way up to I plus 1. Good, check. So we're in state 1. Okay, what about the second case? What if they're not equal? Well, when they're not equal, we flip our to be false. And when we flip it to be false, we do that because we now have evidence that A is not equal to B. So it's true that A is not equal to B because they're not equal in this index. So again, we're good because we end up in the second case. So remember, we had our two cases here, but all we're trying to argue in all these cases that we end up in, technically three, because it's two main cases with two subcases on the second one, we're trying to argue that no matter where we start out, we end up in either one of these two locations. Either R is true and we've confirmed they're all the same, or R is false and we've confirmed that they're not equal. And that's what we've done. So that means we're done. That means we can conclude and say by induction we've shown what we're trying to prove. So this last bit, the postamble, is just saying, hey, we're done. We've proven what we've tried to, and we close it off here saying we've proven what we've set out to prove. So let's once again complete this video with just a quick look at the corollary, which remember is, well, correctness follows from that loop invariant that we just proved, but it follows pretty directly and almost obviously, and oftentimes we would leave out this proof, but I of course include it because we're practicing our proof, so why not? Let's take a look at it. So again, setting up a proof of correctness, we want to start out with generality. Generality in proof of correctness means assuming an arbitrary input, and an arbitrary input for this problem means an arbitrary two strings A and B. So let's assume we have two strings, arbitrary strings A and B, one of length n, one of length m. Now again, like we did in that last proof of correctness, I'm actually going to split it into our two cases. We should either answer yes or no here, right? And so since we should either answer yes or no, we're going to split those into two cases. Should we answer yes or should we answer no? So one way of thinking of that is we'll say, let's assume we should answer yes, then we'll try and argue that we do answer yes. And vice versa, if we should answer no, then we argue that we do answer no. Of course, here I'm using yes and no interchangeably for true and false. All right, so it looks like case one I've decided is say they're equal, so assume they're equal. So assume they're equal. What did our loop invariant tell us? Well, it tells us that after iteration I of the loop, either R is true and they're equal up to index I, or R is false and they're not equal. Well, since by assumption in case one they're equal, we know that in particular after iteration n, R must be true. We can never be false because it could only be false if A is not equal to B and A is equal to B. So after the loop, R must be true. We return R, that's correct. That's what we're supposed to. Okay, what about the other side then? Other side of the coin. Assume A is not equal to B. Okay, we're supposed to answer false in this case, right? Okay, so what does the loop invariant tell us here? Well, again, I'm basically saying the exact same thing above. We know after iteration I, it's either going to be in the true state where they're all the same, or we're going to be in the false state where they're not equal. Since they're not equal, we have to be in the false state. Okay, we can't possibly be in the true state. And so, once again, we return the correct answer, false, in this case. Hopefully, if you're reading through this proof, you're like, that's pretty straightforward and obvious. It should be. It is fairly straightforward and obvious, which is why this proof is often one, I mentioned this is a corollary, meaning the proof is usually a direct and obvious conclusion. So we might just omit it if we felt our audience would also find this proof to be straightforward and obvious, then we wouldn't include it. I just conclude here with a statement. Well, in both of our cases, we output the correct output, so our algorithm is correct for the problem that we posed it for. All right, that brings us to the end of, again, this video. Hopefully this last couple videos or series of videos helped us get comfortable with loop invariance, proofs of correctness, and this new proof style of induction. We are going to have an opportunity to practice induction some more. In fact, the proof style we'll probably practice the most in this series of videos is induction, so we'll see more examples of that coming up. But to do that, I again want to maybe start talking about another subject matter in algorithms and computer science, which is the efficiency of these algorithms. We've talked about their correctness. Now that we've established how correct they are, how can we establish how efficient they are and maybe do some proofs related to that? So stay tuned for that in a future video. And I guess I'll leave it at that there. So thanks again for watching, and we'll see you in that future video.